Hello, welcome, and an excellent evening. Today on Let's Code MS-DOS, we want to take a look at how you program sprites that could be used, for example, in an adventure game, such as Monkey Island 2, which you are seeing here. And I guess most of my viewers, at least of a certain age, will know this game. Adventure games have fallen a bit out of favor. They are still there, but much fewer and far in between. But I consider Monkey Island 2 from 1991 as the pinnacle of classic adventure gaming for so many reasons. One of which is definitely also that the pixel art graphics has aged pretty well, I would say. It has stood the test of time, and as a kid and a youth, I was always wondering, how do you code this? In school, I started to program my own adventure game engine, but didn't get extremely far because I was still learning, and there wasn't an internet to speak of where you could look things up. So I had to guess a lot of stuff. Simple things such as sprites took me weeks to implement correctly. And for example, the games such as Monkey Island 2 introduced something like sprite scaling. You can navigate Guybrush here by clicking around, but once he goes further into the background, like here, he suddenly gets much smaller, which is, of course, makes sense. It's totally normal that people who walk further away from the camera will appear smaller. There's many other things like the animated backgrounds, the parallax scrolling here of this boat or remnants of this boat, and many more things that are cleverly done here. But for now, we want to concentrate on how to animate a character. There's also things like occlusion, which is a thing, pathfinding, because Guybrush follows your clicks and will walk to wherever he can. But for now, we will just concentrate on how to animate a character, at least roughly, and how to scale the sprites. And of course, you can also walk off the edge of the screen without having him appear in the other direction. And there's also transparency. He isn't just a rectangular square, but you can see where his outline is basically. How does that work? You can walk out and it's not simply cut off. Or it is cut off actually, but it's not coming in at the other end or something. Okay, so let's have a look. For this example in this video, I will use this background here. You will probably not have this in the source code because this is copyrighted, but I thought it's nice to use Guybrush actually, and you can certainly get a hold of the assets if you wanted to. So this is our background because this is very nice. You can walk left and right without anything. This is, I think, on Booty Island, the spitting contest, I think. And it's a nice scene for doing some experimentation. We won't do the occlusion, that will be something for the future. And we will use only the right-facing walk cycle of Guybrush. We could flip this around to go the other direction, but we also don't have anything going, looking at him from the front or the back. But this should be sufficient. These 6 sprites are spaced out evenly in a grid of 32 by 48 pixels. I did this manually because the assets that I found were not quite evenly spaced. It was a bit too complicated. But this should work. The green here is just to highlight that this is the background. This will become transparent. The palettes are so that this picture takes up, I think, roughly 160 colors or so at the bottom end of the VGA palette, and Guybrush only takes up 16 or 32 shades of color. I'm forgetting, but something like that. So every sprite has something like 16 colors of their own. So there is a limit to what you can display. But there's definitely room in this image for other sprites to be loaded into, and this will be one of the things that we have to take care of. Then we have to chop up the image here by basically cutting out every single sprite and copying it to its own structure, and then we can draw this on the screen. This time I have left the main program filled because it is quite a lot, but this is mainly handling of the keyboard input, which you already know, and doing a couple of things. Let me walk you through that, also by showing you what we will be implementing. There will be one new header file called sprites.h, which includes a structure, a very simple structure. This might become more complicated later on. A sprite structure with just a width and a height and some data. Not even a palette. That would be a useful addition for sure, but right now it's just width and height. Then we'll implement 5 different functions. A getSprite function, which will store the background that we'll be writing to so that we can restore it, because the PC and simple MS-DOS machines don't have hardware sprites, so everything here is done in software. On the C64, on the Amiga, you could use hardware sprites with other limitations when it comes to occlusion, etc. But most of these games will opt for software sprites because they're more flexible. You can do a lot more things with those. They are computationally more expensive, but also with this comes the fact that you need to store the area underneath the sprite so that you can restore it in the next animation frame. Then we will have 4 different variants of sprite drawing. The simple put sprite, which just slaps Guybrush onto the screen with black pixels in a rectangle and all. The green color that you saw before will be black in that case. Then put sprite transparent, which will do the same thing, but honor the transparent pixels, the green ones. This will do no clipping, so Guybrush will come in on the other end if you walk off the screen. Then put sprite clip, which does exactly what it says. It will clip at the screen borders, which should help with that. And then for the final iteration, we will also allow for sprite scaling, where we can give an integer scaling factor, where 100 is 100%, down to 0%, and then Guybrush vanishes. There will be also a pointer, which points to the buffer that all the sprites will go into. In a future thing, you might want to put all this contextual stuff into like a graphics context or something. But for now, this should be enough. Let's have a look at the main program. The main program will have a bunch of variables that we need, the usual stuff for keyword handling and the game loop, a couple of iteration variables, or actually only one. Then the current position of the sprite, which is not part of the sprite, so that would be something that you could also put in there. X and Y, and the position in the previous frame. We need that to restore the overwritten parts of the image. In the beginning it will be the same, because Guybrush didn't move, but it could be different from frame to frame. Then we have a scaling factor that is 100, so Guybrush will be it's his full size, so to speak. And we have a time counter that we, I think, currently don't use, so please ignore that. And then a byte variable called algo, which is the algorithm. It's 1 for the first put sprite routine, then 2, 3, and 4 for the other ones. You will see that in a second. 2 images will be loaded, the background and the Guybrush sprite sheet, both which I showed you before. Then we have 6 sprites, which will be cut from this Guybrush GIF. And we will have a backup sprite, which is for the background that we overwrite. This will basically just be a temp buffer, so to speak. We are actually drawing directly to the background image, so there's no need to copy that somewhere else. then we go to the graphics mode. We copy the background palette to, no, we don't copy the background palette, we copy the sprite sheet palette, namely 48 colors from that. No, not 48, 48 entries, that's 16 colors. So yeah, it's definitely 16 colors for Guybrush. Into the upper part of the background colors, background images color palette. Then we initialize the palette and copy the whole stuff into the VGA memory. So we do have a screen now. And then we start to allocate our sprite data. And we have a little function called chop sprites, which will cut the sprite sheet into 6 sprites, so to speak. We can look at that actually now. It says here, cuts the sprite sheet into individual sprites. Ideally, the parameters plus graphics data would be stored in a single file, which could be loaded in a single block. So if you want to program a game, think about the data structures and maybe arrange it accordingly. You will probably want to write your own conversion tools in the language of your choice to prepare all the graphics data that you created. Okay, here's some variables where the image starts. It's not standard at the top left because that's the way I downloaded it. And I just moved it horizontally so that the spacing is equal with width 32 and height 48. And then we shift all the image data because the sprites start in the lower 16 colors, but that collides with our background image. So I shift all the color values 176 up. That's what you saw on the palette manipulation. And then we basically just initialize the sprites and copy row-wise from the sprite sheet into the individual sprites. So there's not much magic to that. You can pause the video here and look at the code. It's, I think, reasonably easy to understand. It basically just cuts and pastes all the sprites from the sprite sheet into the individual sprite structures. All right. Then, at first, we need to very first thing, initialize our backup sprite with wherever we are currently rendering. The clamp and clamp X and clamp Y macros make sure that we don't overstep the screen boundaries, otherwise we will store and restore from the other side of the screen, which is in theory fine, but we probably still don't want to do it. Actually, it would be better to do some clipping here as well, but that would have made the code much more complicated. So at the moment, we are trading some efficiency for ease of simpleness of code, so to speak. Then our main game loop. There's our usual keyboard routine, escape, quits. And then with 1, 2, 3, 4, we can choose the algorithm to use so that you can interactively try out the different sprite methods. Plus and minus, as well as equal and underscore for the US keyboards, increases and shrinks the sprite size to a maximum of 100 and a minimum of 10 in steps of 1. Then WASD moves Guybrush around in the horizontal direction a bit faster because that's usually the wider screen size, so to speak, and that's it. And I also put in an interrupt 3 hexadecimal for crashing to the debugger when you hit space. That's good for debugging, actually. This will basically trigger the internal Turbo C debugger. And on modern platforms, it will trigger GDB or whatever you're running. If you're running inside the debugger, that is. Otherwise, it will probably do nothing or generate a code dump or something. Then the next step will be to restore the backup from our backup sprite and get the backup from the new position. You can see here X underscore and X. And then we update X underscore. And then we draw the actual new sprite by switching to the algorithm and choosing our sprite from the sprite sheet by, oh, we actually do use the time counter, by dividing the time counter by 4 modulo 6. This makes the animation a bit slower, so to speak, so that it looks more natural. And every time you press a movement key, the time index is incremented. Very simple. Then we wait for the retrace and copy the whole back buffer to the VGA. We could use mode X or mode Y here and use page flipping. However, the sprite methods would then look quite different due to the way mode X functions, because we can only write every 4th column at a time, sensibly at least, and we would need to rewrite everything. That is a bit too difficult for now, I would say. So that will happen maybe in a later video, but maybe this is all fast enough for most adventure games, even on 286s. Might be a bit slow on XTs, so yeah. Okay, let's have a look at the Sprites implementation. I just set the sprite buffer to the VGA memory as default, but we move it to the background image in the code, as you have seen. So, the sprite routines, most of them, except for the scaling one, will look very similar from the initialization and even from the implementation. First of all, let's write the get sprite routine, which is the same as the put sprite, but with source and destination pointers swapped, so to speak. So we need an iterator variable I for our loop. We need a destination pointer, which will be the sprite data. That's where we write to. And there will be one special thing that we need to talk about. Let's see our preview here. Normally, images and every coordinate system on a PC has its origin on the top left. So this would be sprite coordinate 0, 0. However, due to the way the things work out with the sprite scaling and also with the movement of Guybrush, I decided to put 0, 0 on the bottom right. Then it's easier to position the sprite in a way on the screen that looks reasonably well and maps correctly to the coordinates, because you usually expect him to run around on his feet, so to speak. So we will go through the sprite from bottom to top by copying, and later we will go from right to left row-wise, but we'll come back to that. So we need to add something to the sprite data, because that will point to the top left. So we say, basically, we take the width of the sprite times the height of the sprite, but this will actually point to one after the last byte, and we want to copy most efficiently, in this case using memcopy, row-wise, so to speak. So what we will do here in the loop will be something like memcopy to the destination from the source, sprite with pixels in size. So that means we don't take the, if I zoom in, we don't go from here basically, but we start from here and copy this whole green line, or let's say this is already outside of Guybrush, we'll copy this whole line here using memcopy. And that's why we do the -1 here in the sprite height. You can draw yourself on math paper a little sprite and figure out these indices yourself. That would definitely make sense. What about the source pointer? Well, the source pointer is the sprite buffer, which can be globally changed, plus the x coordinate, wherever we want to put or get the sprite data from, minus, because we're going backwards from the bottom, so to speak, minus the sprite width, because we have to go to the left basically, plus y minus, that's the same as here, y minus 1. Again, we skip the last line, otherwise we end up too far in the memory, times the VGA width. It's a little bit front to back, the whole coding, so if we were expressing it from top to bottom, it would look a little bit easier. Mostly the signs would flip around, but and this will, the sprite width would actually cancel out completely. But I think this has a couple of advantages when placing the sprite. So bear with me, it will all look very similar from here on out. Then we do the loop. We are going sprite width times, sprite height times, so sprite height. We increment our counter and we decrement our destination pointer by sprite width. That means we go to the previous row of the sprite, and we also skip upwards, that is minus equals, the size of the buffer, which is VGA width, which is 320. Okay, that's already our get sprite routine. This does not do clipping, that's why you need the clamp functions to have it not run out of bounds. Then the put sprite function, we can actually copy that whole thing, and it will be basically the same, except that we can swap source with destination. The source pointer will be from the sprite data, sprite width times sprite height minus 1. The destination pointer will be exactly the same, and then we will do exactly the same iteration and do exactly the same mem copy. Just the source and destination are swapped. And that's already everything you need for that. Let's take a look if that will work. There will be a lot of warnings, which we will ignore. And we can load everything, and we have an error here. I have to debug. And most of you probably, hopefully, have seen it already. Of course, I have to swap the source and destination names here as well. And that's why it looked so weird, because we didn't skip backwards VGA width, but only sprite width in the destination buffer. So this time I hope it should look okay. Yes, it does. And yeah, I can move Guybrush around. I can even move him up and down. He doesn't leave any weird trail because we restore the pixel data every time. He of course doesn't moonwalk if he walks back, and he walks the same up and down as he does back and forth. But if we go to the left side, he will come in on the other side, and that's of course not cool. Plus the restoring will break down because we're clamping that. Same if we go down, then we come up somewhere at the top and leave some smear behind. So this is not the be-all end-all of things, but it's a start. We do have kind of a sprite moving around. So next up will be the transparency to make it look a bit nicer. The initialization will look very, very similar. So let's copy the whole block here. But we can't do a mem copy. The mem copy can't do a conditional copy of individual bytes, depending on which color they are, and then leave transparency unset and stuff like that. However, most of the things here will look very similar, but we can actually do it a little bit simpler even now, because we can now really start at the bottom right and just go backwards through the image. So the source will be the data pointer plus the sprite width plus sprite width times sprite height minus 1. That is actually quite okay, except that we start from really the last pixel, but this points to 1 pixel after, so we do a minus 1, and then we end up right on the last pixel in the sprite. This will point exactly to here where the mouse cursor is, and without the minus 1 we would be slightly outside of the sprite, which would be a bad thing, so to speak. The destination buffer will similarly be the last line that we need to work on. Actually, we will leave out the sprite width because that was shifting us to the beginning of the line. This here is okay. And again, we need to subtract 1 to hit the last pixel inside of the target region, so to speak. We will also have a much simpler loop, so to speak. The destination will be decremented as usual by the length of a VGA row, so to speak. And minus the sprite width, because that is something that we already skipped ahead of, so to speak. And that is it for the outer loop. This is the loop over the rows, so the vertical direction. And we will need another iteration over the horizontal pixels. This will basically be the columns. So j equals 0, j less than sprite width plus plus j. And here we will decrement the source pointer as well as the destination pointer. And this also explains why we will subtract this here. Otherwise we would skip too far ahead. And then of course we don't do we don't do a mem copy here. That is not possible. But we do something like this. If the source pixel is not equal to 0, then we will write it to the destination. Just like that. And I think this should be good. Shall we try it? I'm not sure if I made a mistake or not. So this is our usual Guybrush, and then we switch to algorithm number 2. And yes, it works. So now we have a transparent Guybrush, which already looks pretty decent, I must say. This looks pretty convincing, right? But if we go outside here, you can see him coming in on the other side again. And going back, yeah, similarly. We can also go down here and then he will come up all messed up there. So there is more to do. We need to have some clipping, which is not that difficult to add. We can use the transparent algorithm as a basis. It needs some more adding. We must not simply write the pixel if it's not the 0 pixel, but we should also check some other things. So we only do this if there is some color data here to be written, and if the x minus j coordinate, that is the actual current screen coordinate that we are working with, is bigger or equal to 0, because we are 0 based. And if x minus j also is less than or equal to the VGA width. And the same, of course, for the y direction. So if y minus I actually, and y minus I, and of course compared to the VGA height, then and only then we can write to the screen. This should give us perfect screen accurate clipping. So let's check. There's an error because I copied the and there. And looking at that, this is with the clipping not enabled. Yeah, now I go to clipping, and there you go. Yeah, we have a off by 1 error, it seems. So I have to check that. There's probably one thing where I went wrong, but from top to bottom it seems to work. Let's walk up here. This also works. So we have an issue here on the left side, then he comes in on the right, which is of course not what we want. And on the right, this is looking good. This is looking fine. There's nothing coming in from the other side. So this is neat. So what did we do wrong? Let me quickly check. Very weird. For some reason I need to go x minus j greater than 0 here. If we do that, Guybrush behaves perfectly fine. I will look at this probably afterwards and post a hopefully bug-fixed version, because that shouldn't be the case. I'm wondering what I did wrong here, because I didn't have this issue in my tests. But maybe I miscalculated something or other. I don't know. But the principle is the same. You need to use the current sprite pixel index to adjust your screen coordinates and then test for the screen boundaries. That's what's happening here, basically. And now for the grand finale. Let's try to do some scaled sprites. That is quite a bit more involved. The source and destination pointers will be very much the same. We also need the same variables here, but the other stuff is very much different. So what else do we need here? We need a bunch of new variables, but we'll look at that. The idea is that we do some kind of linear interpolation, similar to what we did when we learned how to draw lines. When drawing lines, we computed the slope of the line and used that as an error accumulation variable. And every time we added up the error variable, and when it overtook a certain amount, we would know, okay, now we have to skip to the next row or column on the screen to make the line go into the correct direction. And that was the Brazenham algorithm. A very similar thing is happening here. We take these variables as x and as y as scaling factors for x and y, and we will need some kind of error variable which, if they exceed 100, it will mean we need to do the next drawing, basically. Otherwise, we skip the intermediate pixels. This way, it will draw things much smaller. The error accumulation variables will be called, or the error corrected pixel coordinates will be ex and ey. We start off with these already at 100 so that we definitely draw our first pixels. If you don't do that, this thing will still render, but you will probably miss out on the first row and or column, and that's not what you want. Okay, that sounds pretty abstract, I know, but let's go ahead. First of all, we're again doing the column, the rows first. So for I equals 0, I less than sprite height -1. Actually, otherwise we draw too far, but this is down to the maths. It's a bit complicated to explain. Not sure I could do it from the top of my head. Oh, actually not, because we are running backwards and going to 0. So otherwise we would have one too many here. Yeah, that's actually garbage what I wrote here. Sprite height -1. So because we're running backwards, not forwards. Then we need to decrement our I, obviously, and the error accumulation variable will be incremented by our scaling factor as y. And this means, for example, that if you set it to 50, every other row will be skipped, because only every other row we will have a value of 100 and do the actual drawing. So similarly, the inner loop will look very, very similar to this. But if the error variable meets or exceeds 100, we need to do the actual drawing. If that is not the case, we have the case that we actually skip this current line. So we subtract sprite width from our source pointer. That means we skip the whole row of pixel values. But if we are supposed to draw something, we will reset the error accumulator by subtracting 100. Then we will set our error corrected screen coordinate, because we have arrived at a new row, so to speak, to 0. This is our error corrected screen coordinate. And then we do the inner loop. After the inner loop, we can finally skip in the destination buffer the whole VGA width minus how many pixels we drew, and that's the EX value. EX will be counted in the inner loop. And then we can skip to the next screen line, so EY++. All right. This also shows that in the case where we skip, we don't advance on the screen, basically. So next up, what does the for loop look like? We initialize this here with the sprite width. We are also going backwards. -1, same reasoning here. J must be greater or equal to 0, so we're walking downwards, and this will give us a loop of exactly length sprite width. Then we need to count down J, of course. We need to count down our source variable, because we're going to the next sprite pixel. And we have to increment our error corrected our error accumulation variable for the x direction. And here we have the very same principle. If this error accumulation variable exceeds 100 or meets 100, that's good enough, then we have to actually draw something. So we correct our variable again to reset it. Then we check our screen coordinates if they lie within the screen. This is basically the clipping part. X minus the error corrected -1 must be greater or equal to 0. And x minus ex -1, this is the real screen coordinate, so to speak, must be less than VGA width. And now the y direction, y minus the error corrected screen variable, must be greater than 0, and y minus ey must also be less than VGA height. And of course, the transparency, if there's any source color there. Then we can actually write the destination value by taking the source value. When that is all done, we can skip to the next destination byte and also update our error-corrected screen coordinate. And that is it. That is the whole magic of the sprite scaling. Let's first test it if it works. And if it works, we can go one more time through it. So this is the sprite scaling. It seems to work, at least on a basic level. Now press minus, and indeed, we can shrink Guybrush up to a very small size. It looks quite funny. I think this is actually, I mean, you can see that there's rounding errors and stuff, so there's probably better algorithms to do that. But it's a relatively fast one, I would say, and it looks convincing enough. For example, if I place Guybrush back here, he looks like a giant. But I can shrink him down, and of course we don't have occlusion, but it would work in a game like that, I would say. Here in the middle background, I would say he probably should look like something like this, maybe. And this looks pretty decent, I would say. And the screen clipping should function just fine, yes, even in the scaled version, so he can go off screen without looking weird or smearing around. And I can enlarge him again. Yeah, that's pretty neat. I would say this is a good start for an adventure game engine. So let's recap one more time. So the whole trick here, and you could even scale the sprite in X and Y direction differently and do some funky effects. The whole idea here is that we have these error accumulation variables, EI and EJ, plus the error corrected screen coordinates, because we only change those if the error accumulator overflows. And that's happening in both directions. So we go from the bottom right to the top left in the sprite in an outer variable from bottom to top, and an inner loop, of course, from the right to the left. And only whenever one of these accumulators overflows, we reset it, we update the coordinates, and then we do all the other tests with the screen clipping. So actually not that difficult. So I think we can definitely build on that and do more complex stuff. We had the clipping, no, not the clipping, the very simple sprite function without transparency. Then we added transparency without any clipping. Then we added the clipping, and then we added clipping and sprite scaling. So that's it. But that is all. The link to the source code is in the video description. You just need to supply your own assets. And as always, thank you very much for watching. Leave a comment. What is your favorite adventure game? Did you ever try to implement something like that? And yeah, share, like, and subscribe. You can follow me on Mastodon as usual on chaos.social/@root42. I'm very active there and usually answer most of the messages that I get. And yeah, see you next time, I would say, and bye.